Have you ever thought that antiderivatives and integrals are the same thing? Think again. The truth might surprise you. What if I told you that what you learned in calculus might not be the full story? Stick around, and I'll show you what's missing, and how it might just change the way you look at math forever. Let's explore this. Antiderivatives and integrals are related concepts, but they are not identical. While antiderivatives involve finding a function whose derivative gives you back the original function, integrals deal with the area under a curve, or the accumulation of quantities. Imagine you're working with two functions, big F of x and little f of x, where big F prime of x equals little f of x. In this case, big F of x is the antiderivative of little f of x, and little f of x is the derivative of big F of x. The antiderivative is simply the reverse process of differentiation. Let's see some examples. The derivative of sine of x is cosine of x. So, the antiderivative of cosine of x is sine of x. The derivative of the natural log of x is 1 over x. So, the antiderivative of 1 over x is the natural log of x. Sounds simple, right? But here's the twist, antiderivatives are not unique. Why? Because the derivative of any constant is 0. For instance, the derivative of the natural log of x is 1 over x. The derivative of the natural log of x, plus 5, is also 1 over x. An antiderivative of a function, like little f of x, is any function, such as big F of x, whose derivative equals little f of x. For example, an antiderivative of 3x squared could be x cubed, or even x cubed plus 5. However, the antiderivative of little f of x is generally expressed as big F of x plus c, where c is an arbitrary constant. This constant represents the infinite number of possible antiderivatives. For instance, the antiderivative of 3x squared is x cubed plus c. Why are antiderivatives useful? Antiderivatives allow us to solve real-world problems where we know the rate of change, or derivative, and need to find the original quantity. Imagine this: you throw a basketball straight up into the air. Gravity pulls it back down with a constant acceleration of approximately -10 meters per second squared. If the basketball's initial velocity is 60 meters per second, how can we determine its velocity at any moment in time? Here's how. The antiderivative of -10, with respect to time t, is -10t plus c. Now, let's use the initial condition. When time equals 0, the velocity is 60 meters per second. Substituting these values, we find that c equals 60. And there you have it, the complete equation for velocity, v of t equals -10t plus 60. This equation allows us to find the velocity at any moment in time. In summary, an antiderivative reverses differentiation, but it always includes an arbitrary constant. It's a fundamental concept in calculus, with many applications in mathematics and science. What is an integral? Well, integration is a powerful tool in mathematics. It's used to calculate the total amount of something. It helps us find areas, volumes, and the total change of a quantity over time, by adding up infinitely small pieces. To understand integration, let's look at finding the area under a curve. Consider the function f of x equals x squared. We want to find the area under this curve from x equals 0 to x equals 2. Now, here's the catch. There's no simple geometric formula to calculate the exact area under this curve. To approximate the area under the curve of f of x equals x squared from x equals 0 to x equals 2, we divide the region into two rectangles, each with equal widths. The width of each rectangle is delta x, which equals 1. Next, we determine the height of each rectangle. To do this, we look at the right edge of each rectangle, find where it crosses the curve, and use that point to determine the height of the rectangle. It's a simple process, but it's essential for ensuring the accuracy of our approximation. The key idea here is that the height is based on where the curve intersects the rectangle's right edge. This helps us approximate the area under the curve. For the first rectangle, the right edge is at x equals 1. The height is given by the value of f of x equals x squared at x equals 1. That is, 1 squared, which equals 1. So, the height of the first rectangle is 1. Similarly, for the second rectangle, the right edge is at x equals 2. The height is given by f of x, which equals x squared, at x equals 2. That is, 2 squared, resulting in 4. Thus, the height of the second rectangle is 4. To estimate the area under the curve, we add the areas of two rectangles. The area of a rectangle is given by its height, multiplied by its width. Here, the width of each rectangle is delta x, this equals 1. For the first rectangle, the height is 1, and the width is delta x, which equals 1. So, the area of the first rectangle is the height times the width. That's 1 times 1, which equals 1. For the second rectangle, the height is 4, and the width is delta x equals 1. So, the area of the second rectangle is height times width, which is 4 times 1, equals 4. Finally, to approximate the total area under the curve, we add the areas of the two rectangles. The total area is 1 plus 4, which equals 5. However, as you can see, our approximation overestimates the true area under the curve of f of x, which equals x squared. This happens because the tops of the rectangles extend above the curve. We included this extra portion in our calculation, even though it should not be part of the actual area under the curve. To get a better approximation of the area, we can reduce this extra portion. How? By dividing the region into more rectangles with smaller widths. This approach makes the rectangles fit the curve more closely, reducing the overestimation. As the number of rectangles increases, and their widths approach 0, the total area of the rectangles gets closer and closer to the exact area under the curve. This amazing concept forms the foundation of integration. It allows us to find the precise area under a curve, mathematically and accurately. What we've done so far is called the right sum. Why? Because we selected the height of each rectangle based on the right endpoint of each interval. But guess what? We could also calculate the area using the left sum. This time, we would select the height of each rectangle based on the left endpoint of each interval. Interesting, right? As you can see, the left sum underestimates the true area under the curve, while the right sum overestimates it. Both methods provide approximations. However, the error decreases dramatically as we divide the interval into more rectangles. To calculate the true area under the curve, we use the limit of a sum. First, we divide the interval into n rectangles. Then, we take the limit as n approaches infinity. The area of each rectangle is determined by the function value at the right endpoint of each interval. Now, let's take a closer look at the formula, and make it a little better. Remember, we are calculating the area under the curve for this simple function, f of x equals to x squared. And yes, even for this simplest function, it seems like we are facing a very tough challenge. To simplify things, we take delta x outside of the summation, since it is the same for all the terms. What we're left with is the summation of infinitely many function values. To reflect that we are working with a limit sum, we introduce a special symbol. Instead of writing the summation symbol, we stretch the letters, which stands for sum, vertically. This creates a new symbol that tells everyone we're using the limit sum. This is the integral sign. The stretched S symbolizes that we're summing up infinitely small contributions. Next, we replace delta x with dx, which reflects that the width of the intervals is now infinitely small. Since the summation is over infinitely many points, we no longer use discrete values, like f of x sub I. Instead, we simply write f of x, to show the continuity. This gives us the integral representation of the area under the curve, the one we are familiar with. Finally, because we are calculating the area over the interval from 0 to 2, we indicate this with the limits of integration, 0 and 2. Now, we have a formula for the area under the curve. It's written as the integral from a to b of the function f of x, dx. This computation gives us a single value. It represents the area under the curve. We call this the definite integral. But what about the indefinite integral? The indefinite integral can be thought of as a definite integral, where its upper limit is a variable. We write it as I of t equals to the integral from a to t of the function f of x, dx. However, we often write it without the boundaries, like this, the integral of f of x, dx. The result of an indefinite integral is not a number, like the definite integral. Instead, it's a function. So, to summarize, a definite integral gives a specific value, like the area under a curve from one point to another. An indefinite integral, on the other hand, gives a function. It represents the accumulation of values up to a variable upper limit. This distinction is crucial. It helps us understand how integrals can be applied in different ways, depending on the context. Now that we have the definite integral, it allows us to calculate the area under the curve of f of x, within a given interval. But here's an important point. The concept of an integral is fundamentally different from the concept of an antiderivative. An antiderivative reverses differentiation. An integral, on the other hand, sums small parts to find a total, like the area under a curve. So, we can confidently say this: an antiderivative is not the same as an integral. You might be wondering, if antiderivatives aren't the same as integrals, why are we told to use antiderivatives to calculate integrals instead of relying on the limit sum? Well, this is possible because of one of the most famous theorems in calculus, the fundamental theorem of calculus. The fundamental theorem of calculus bridges the gap between antiderivatives and integrals. It has two parts. First, the indefinite integral of a function, f of x, is the same as its antiderivative. In other words, the integral of f of x, dx, equals big F of x plus c, where the derivative of big F of x is equal to little f of x. Second, the definite integral from a to b can be calculated using the antiderivative. This means the integral from a to b of little f of x, dx, equals big F of b minus big F of a. This makes finding areas under curves so much easier. Instead of summing up infinitely small pieces, we use antiderivatives as a shortcut. But, remember this: it doesn't mean integrals and antiderivatives are the same. Let's use a simple analogy to clarify the difference. Think about finding the area of a shape. The area of a circle is given by pi times r squared. Meanwhile, the area of a square is s squared, where s is the side length. Now, if a circle and a square happen to have the same area, does that mean their formulas are the same? Of course not. They're just two different ways to arrive at the same result. For example, the area of a square, with a side length s equal to r times the square root of pi, is exactly the same as pi times r squared. Similarly, antiderivatives and integrals are different processes. They can lead to the same answer. The fundamental theorem of calculus connects these two ideas, making integration faster and more efficient. But, it's important to understand, they are conceptually distinct. At Mitra Institute of Education, we understand that these nuances in learning can make a huge difference in your academic journey. That's why we're here to help, whether you're in kindergarten, preparing for college, or writing your thesis and defending it. Our team? A dedicated group of PhD educators with years of experience, ready to guide you every step of the way.